This tutorial explores the topic of analog signal conditioning for electronic sensors within the framework of the European project, titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. The measurement chain for the digitalization of any physical quantity should follow the path represented in the figure. So, the analog sensors and transducers give a relationship between the quantity of interest and the variation of an electrical quantity, such as a voltage, a current, or an impedance. However, the digital conversion of an analog signal can convert input voltages to digital waveforms. Therefore, it is necessary to have a conversion block between any electrical quantity and a voltage that can be measured through a data acquisition board. This block is usually called the analog signal conditioning stage and represents the electronic circuitry that converts an input electrical quantity to a low voltage signal of the order of a few volts. As previously mentioned, the output of a transducer can be any electrical signal, while the input of the analog to digital converter is a voltage. The signal conditioning is therefore the actor who converts the transducer output to a voltage. It has to be remembered that the measurement system does not have to load the measure and, otherwise it will change the measured value. Before going into the details on the different kinds of signal conditioning structures, it is worth reminding ourselves how an operational amplifier works. In fact, due to its infinite impedance at the input, it acts as an infinite load to the input voltage, while having an output impedance theoretically zero. The main properties are the following. Ideally, the output voltage is infinite and is proportional to the difference of the input voltages at its inverting symbol minus and non-inverting symbol plus terminals. The input impedance is infinite, so that it drains a zero current from the main circuit, solving the problem of loading its input. The output impedance is equal to zero, so it supplies the current necessary to maintain the voltage at its output equal to Vout. The easiest configuration of an amplifier is called a buffer or voltage follower. In a buffer configuration, the output is directly fed back to the inverting input, resulting in a unity gain amplifier. That means the output voltage matches the input voltage exactly. Even though there is no amplification in terms of magnitude, the buffer plays a critical role in signal conditioning. It provides very high input impedance and very low output impedance, allowing it to isolate one stage of a circuit from another without loading the previous stage. With this configuration, the signal at the input V+ is forwarded unchanged in amplitude, but without draining the input. When one wants to have the output voltage with a gain different than 1, some specific configuration can be adopted. The first is called non-inverting configuration. In this case, the inverting pole is connected to the ground with a resistance R1, while the feedback impedance is equal to R2. Since the current should be the same in both resistances 1 and 2, and due to the virtual connection V+ equals V-, it is easy to get that the ratio between V- and R1 equals the ratio between Vout and R1 plus R2. The gain is calculated as the ratio between Vout and Vin, and so it is equal to 1 plus R2 divided by R1. Because the input does not pass through the resistor network, this configuration offers an infinite input impedance, ideal for sensors or high-impedance sources. On the other hand, in the inverting amplifier configuration, the input signal, Vin, is applied through a resistor, R1, to the inverting terminal, marked quote, while the non-inverting terminal is connected to ground. This grounding ensures that the reference point of the amplifier remains fixed, allowing the circuit to accurately process signals fed through the inverting side. The output signal is routed back to the inverting input through resistor, R2, creating a feedback path that stabilizes and defines the gain of the amplifier. Because the feedback is connected to the inverting terminal, the resulting output voltage, Vout, is the amplified but phase-reversed version of the input signal. The magnitude of this amplification is controlled by the ratio of the two resistors, expressed as the gain, R2-R1. This negative sign emphasizes the 180-degree phase shift introduced by the configuration. The inverting topology is commonly used when precise, predictable gain is needed, especially in signal processing stages where phase inversion is either acceptable or required. Another useful configuration is the differential amplifier. This could be particularly suitable for measurement signals, since the voltage has to be measured not using only one terminal, or single-ended configuration, but in the differential one. This will be better explained in the Data Acquisition Board tutorial. This mode is used when the intention is to amplify the difference between two input signals rather than amplifying just one. In this configuration, both inputs, V1 and V2, are applied through identical resistors, R1, ensuring symmetry in how the amplifier receives each signal. The feedback network, formed by two resistors, R2, maintains balance and defines how strongly the output responds to changes in the input difference. The key feature of a differential amplifier is its ability to reject disturbances that appear equally in both inputs. This property is also known as common mode rejection. When V1 and V2 change together by the same amount, the output ideally remains unchanged. However, any difference between them is amplified and appears at the output as Vout. This makes differential amplifiers essential in situations where noise or interference affects both inputs equally, such as sensor measurements or long transmission lines in noisy environments. Unfortunately, the output matches the difference of the input voltage with the gain equal to R2 over R1 only if we find a pair of identical resistances. Of course, this is never possible, so a common mode is generated at the output of the amplifier. Moreover, in this case, the load impedance at the input of the amplifier is no longer equal to 0, but there are the resistors R1 that load V1 and version 2. Moreover, the gain is fixed, and, to change it, we have to replace two resistors. Therefore, the differential amplifier is an interesting approach, but with some limitations that make it not the best option. One may add a buffer at the input of V1 and V2 to also overcome these last problems. However, the operational amplifier has a characteristic that limits either its bandwidth or its gain. In particular, the GBW gain bandwidth product is fixed, which means that if we increase the gain, we should reduce the bandwidth and vice versa. For this reason, it is useful to increase the complexity of the differential amplifier, not by adding simple buffers, but by adding two more amplifiers, as in the figure. In this case, we have a cascade of amplifiers before the differential amplifier. This configuration is usually called an instrumentation amplifier. The first stage ensures infinite impedance at the input of the amplifiers, while the second stage amplifies only the voltage difference between the inputs while rejecting any common mode noise shared by both lines. Because of its excellent common mode rejection and adjustable gain, the instrumentation amplifier is a preferred choice in biomedical sensors, strain gauges, and high-accuracy industrial measurements where precise differential data must be extracted from noisy environments. Now let's focus on the assessment of the gain of the instrumentation amplifiers. Let's consider that the two initial amplifiers receive input voltages, V+ and V-, producing buffered outputs, V1 and V2. These two outputs are linked by resistors R and an adjustable gain-setting resistor RA, allowing precise control over the amplification factor without disturbing input balance or input impedance. The gain of the first stage, which determines how much the difference between V+ and V- is amplified, depends mainly on the value of RA. As RA decreases, the amplification increases, allowing even small differences between inputs to become more detectable. Now, let's zoom in on the first stage of the instrumentation amplifier to clarify how its gain expression is derived. The two operational amplifiers receive inputs V+ and V-, and their outputs V1 and V2 are linked by two equal resistors R and an adjustable resistor RA. Because of the symmetry and the high gain of the op-amps, the voltages at the inverting and non-inverting terminals of each amplifier become nearly equal, establishing a relationship between V1, V2, and the input difference. By applying basic circuit analysis, Ohm's law, and the principle of virtual short in op-amp configurations, the gain of this stage can be expressed as a function of ein function of R and RA. It can be stated that the differential output is proportional to the given formula. This formula highlights the practical advantage of the instrumentation amplifier. Engineers can adjust R_A to set the gain precisely without impacting the input impedance or the matching of the other resistors. To complete the derivation of the instrumentation amplifier gain, it is necessary to combine the contributions of both stages. The first stage, formed by the two op-amps and the resistor network with R and RA, produces intermediate node voltages, V1 and V2, whose difference is already an amplified version of the input voltage differences. These nodes then feed a classic differential amplifier built with resistors, R1 and R2, which further scales the differential signal while rejecting common mode components. Putting the two stages together leads to the final expression for the output voltage. This formula explicitly shows how the overall gain is the product of the first stage gain, set mainly by RA, and the second stage differential gain, set by the ratio R2/R1. In practice, R1 and R2 are often fixed, precision-matched resistors to preserve accuracy and common mode rejection, while RA is adjustable to tune the amplifier for different measurement ranges without disturbing input characteristics. Instrumentation amplifiers provide high input impedance on both inputs, minimizing the loading effect on the signal source and ensuring that even weak signals can be measured accurately. Another defining characteristic is the ability to set and adjust gain using a single resistor without disturbing impedance or symmetry. These amplifiers are designed for accurate amplification of low-level differential signals in environments where noise is significant, making them ideal for medical equipment, strain gauge sensors, and other sensitive instrumentation applications. So far, we have only considered voltage measurement. Let us now discuss the scenario in which the current must be measured. Unlike the voltage, which can be measured directly across 2 points, current must pass through a known element to be measured. In most practical systems, this involves placing a resistor, often called a shunt, in series with the load so that the voltage drop across it can be related to the current flowing thanks to Ohm's law. Accurate current measurement forms the basis of power monitoring, motor control, battery management, and fault detection systems. Understanding how to sense and convert current into a measurable voltage signal enables amplification, conditioning, and later digitization for real-time monitoring and control. To do so, a circuit is used to convert an input current into a proportional output voltage. On the left, a current source represents a sensor, such as a photodiode, often accompanied by a parallel resistor that models the Norton equivalent circuit of the input transducer. This current is fed directly into the inverting input of an operational amplifier. The non-inverting input is connected to ground, fixing the reference potential. A feedback resistor R connects the output back to the inverting input, forcing the op-amp to maintain a virtual ground at that node. As a result, the entire input current flows through R, generating a voltage drop that the amplifier presents at the output as Vout. This configuration is crucial whenever precise current-to-voltage conversion is required, for example in optical receivers, charge sensors, and low-current measurement systems. Starting from the previous configuration, the charge amplifier is done by adding a parallel capacitor to the feedback resistance. On the left, the source represents a device such as a piezoelectric sensor, which responds to mechanical stress by producing a change in charge, delta Q. This charge is fed into the inverting input of an operational amplifier, while the non-inverting input is tied to ground, establishing a stable reference point. In the feedback path of the amplifier, a capacitor C and a resistor R are placed in parallel. The capacitor is the key component. The input charge accumulates on it, generating an output voltage proportional to delta Q divided by C. The resistor provides a discharge path for the capacitor, defining the decay time and allowing the circuit to respond to slow variations as well. Charge amplifiers are commonly used with piezoelectric transducers, where direct voltage measurement would be unreliable due to high impedance and charge leakage. Another use case would be measuring the impedance, namely, if the transducer's output is a change in its impedance. The easiest way is to measure both current and voltage, and to compute the ratio between the two values, which we have already studied how it can be measured. This way is usually called voltamperometric measurement. Another method which provides an accurate measurement of the impedance is called a measurement bridge. The principle relies on balancing a bridge network, typically the Wheatstone configuration, so that no current flows through the detector branch. When balance is achieved, the ratio of two known impedances equals the ratio involving the unknown one, allowing us to compute its value without requiring a large current through the device under test. Because measurements exist at the balance condition, the system is minimally influenced by loading effects, which improves precision dramatically. This approach is widely used when high accuracy is required, especially for components like resistors, capacitors, and inductors across a range of frequencies. By substituting reference components with known values, we compare and solve for the unknown impedance algebraically. When AC sources replace DC excitation, the bridge can measure both magnitude and phase, enabling full characterization of complex impedance rather than only static resistance. Finally, another use case would be an impedance-to-frequency converter, a technique that transforms variations in impedance into corresponding changes in oscillation frequency. Instead of directly measuring voltage or current, the system embeds the unknown impedance inside an oscillator loop, typically involving an op-amp or comparator. As the impedance changes, it alters the oscillation conditions, most often the RC time constant, resulting in an output frequency that tracks the component's value. This method becomes particularly useful when digital acquisition is preferred. Rather than digitizing an analog amplitude, the system measures a frequency, which can be counted with high resolution even in noisy environments. These converters are widely used in capacitive or resistive sensors, where small variations in impedance are converted into easily measurable frequency shifts, enabling precise sensing even with simple electronic readout stages. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.